In this session, we're going to look at inferential statistics. With inferential statistics, you're trying to reach conclusions that extend beyond the immediate data alone. For example, we use inferential statistics to try to infer from the sample data what the population might think. Or we use inferential statistics to make judgments of the probability that a difference between two groups is a dependable one, or one that might just have happened by chance in the study. Thus, we use inferential statistics to make inferences from our data to more general conditions, whereas we use descriptive statistics simply to describe what's going on in our data. What we're going to cover in the session is the rationale for conducting a statistical test, how we go about choosing a statistical test, interpreting significance levels, and we'll look at type of inferential statistics, which involves using parametric tests. Before even thinking about statistics, we need to think about what our research question is. We need to think about what variables we have and what possible relationships there might be between them. So I'm going to use a question that was used in a student research project, and it concerned the relationship between the amount of quality of sleep and people's general health measured by their self-rated health. So let's look at the types of questions that we might ask. We could ask a question like, what is the relationship between sleep and illness, without specifying any direction? We could then ask, what's the influence of sleep on health? But it became apparent during the research that it's also legitimate to ask, what's the influence of illness on sleep? People in poor health, for example, might sleep less. And what about the relationship of other variables, for example, age and the amount of exercise? So what seemed like a simple question at the start of the research became more complex, and this was even before considering what kind of statistical analysis were necessary. So it's very important to specify what exactly it is that you're interested in before you even begin to think about using statistics. Here's another example from a study that I did, and this was a study looking at the effect of receiving hypnotic drug prescriptions on mortality. Without going into the background too much, there's definitely some concern that hypnotic drugs could be causing mortality. However, it's not simple, it's not an easy task to analyse the effect of hypnotic prescriptions on mortality, because clearly hypnotic drugs are often given people to have illnesses already. So the study that I was involved with tried to evaluate model 1, which was, do hypnotic prescriptions make people iller, and then this causes mortality? Or is it the case that people are iller, get hypnotic prescriptions, and that's the reason for increased mortality? So we developed a model which is described in quite a lot of detail in this paper here, which was a way of controlling for all the illnesses that might be a factor in analysing this relationship. So the first thing that we do in the paper is present the reader with descriptive information about the people that received hypnotic drugs, of whom there was 34,000, compared to a matched sample who didn't receive hypnotic drugs. So people were matched on age, gender, and the general practice. So there won't be much difference between age and gender and general practice. So we can take them out of the equation as factors. But let's look at, for example, at smoking status. We see that among the the users of hypnotic drugs, 25% were current smokers compared to only 15% of non-users. So we can see already that there's one factor that could be part of the equation leading to increased mortality. And in this table, we're also looking at differences in baseline mortality in a whole range of conditions, arthritis, musculoskeletal problems, etc. And in every case, you can see that the percentages who use the drugs have higher rates of these conditions. And this last column here shows the statistical significance. So we're using inferential statistics to see whether there is a difference. And in every case, you can see that there is a difference. So this is important to recognize that the users of hypnotic drugs have much higher levels of baseline conditions, which could be leading to increased mortality. You'll often read in papers that the authors state that they used parametric tests. So what do we mean by parametric tests? Parametric tests relate to situations where the data is either demonstrated or thought to be normally distributed. The term parametric was defined in 1942 as distribution functions of the variables are assumed to be of a functional form. And if we plot a frequency histogram, we'll see the characteristic shape of an upside down bell. And the normal distribution has some special characteristics that are very useful when it comes to statistical tests. We're going to look at the normal distribution now. I'm sure many of you are familiar with it already, but if you're not, I'll just go through some of the key points. This figure here shows the normal distribution calculated from diastolic blood pressures of 500 men, and it has a mean of 82 mmHg and a standard deviation of 10 mmHg. The standard deviation is a measure of how spread out the data are. So first of all, we can see the shape of the curve here with just a few observations at the tails in both the left and right. We can see the mean here, and down here we can see the mean plus or minus 1 standard deviation, the mean plus or minus 2 standard deviations, and the mean plus or minus 3 standard deviations. So the first thing to say is that many measures ranging from psychological to physical phenomena can be approximated to varying degrees by the normal distribution. About 68% of values drawn from a normal distribution are within 1 standard deviation away from the mean, shown here. About 95% are within 2 standard deviations from the mean, and about 99.7% lie within 3 standard deviation for means. And this is sometimes known as the 68, 95, 99.7 rule, or the empirical rule. So here we see the normal distribution again, with the 68%, 95%, and 97% relating to 1, 2, and 3 standard deviations. And here, over here, we can see normal distributions, but where the data is clustered more towards the center and dispersed where it's more towards the tails. And here we can see the effects of these distributions. So we can still use the principles of standard deviations, and we can see how in the different distributions we see the effect on the range of the data, plus or minus 1 standard deviation and plus or minus 3 standard deviations. So by knowing the standard deviations, we can understand the characteristics of the spread of the data. The normal distribution is central to parametric statistics. Imagine that we're looking at the blood pressure of people who have or who have not taken ACE inhibitors. So the people who have taken the ACE inhibitors are represented by the blue distribution here, and the people who have not taken ACE inhibitors are represented by the red distribution here. And the people who have taken ACE inhibitors have lower blood pressure, so their distribution is over to the left. And we can see that in all three cases shown by the different graphs, the difference between the population mean is the same. So the difference between the blue and the red line is the same. But what's important to look at is the overlap between the two distributions. So we look at the case where there's high variability. We can see there's a very high degree of overlap between the two distributions. On the other hand, if we look at the ones with low variability, we can see that there's much more separation between the two distributions, and that's what we're interested in when we begin to apply statistical tests. Now we're going to look at the standard error of the mean, sometimes abbreviated to SEM. This is a measure of spread, and it's similar to the standard deviation, but there is one important difference. The standard deviation measures the amount of variability or dispersion for a subject set of data. So imagine we take a sample of data shown by these different samples here. These are all samples of data drawn from an overall distribution which we can't observe, the overall population. So you can see these are normally distributed, and they all have different means because they're different samples, and the standard error of the mean is represented down here. So you can see that these samples are themselves drawn from a normal distribution. So the standard error of the mean is always smaller than the standard deviation. One way of thinking about it is the standard deviation measures the amount of variability or dispersion for a subject set of data, while the standard error of the mean measures how far the sample mean of the data is likely to be from the true population. So standard deviation refers to samples, and standard error refers to the entire population. So just to reiterate that, we use the term standard deviation when we're talking about distributions either of a sample or a population. We use the term standard error when we're talking about an estimate taken from a sample. If we want to say how good our estimate of the mean, for example, of forced expiratory volume shown down here is, we quote the standard error of the mean. If we want to say how widely scattered the data are, we quote the standard deviation. So that's the key difference. One's relating to the confidence interval of the mean, and one's relating to how scattered the data are. So if we look at the slide here, we can see the calculation. Here we have a measure from 57 males of forced expiratory volume, has a mean of 4.062 and a standard deviation of 0.67. So we divide the standard error, by the square root of the sample size, and we get this value here, 0.089. So the standard error of the mean is always smaller than the standard deviation. So that's worth remembering when we look at confidence intervals. We'll have a review question now. The question is, what percentage of the normal distribution lies within two standard deviations of the mean? Is it 50%, 68%, 95%, or 99%? Those are the four answers to think about. And the answer is that it's 95%. One standard deviation is 68%, and 3 standard deviations is 99%. So for 2 standard deviations, it's 95% of the data. We'll have another review question, and this time relating to the standard error. So for a sample mean, the standard error is which of the following? Is it the mean divided by the square root of the sample size, the square root of the sample size divided by the standard deviation, the standard deviation divided by the square root of the sample size, or the standard deviation divided by the sample size? So which one of those four options is it? So we saw in an earlier slide that the way to calculate the standard error of the mean is to divide the standard deviation by the square root of the sample size. Now we're going to look at how the standard error relates to the confidence interval. For normally distributed statistics, the formula for the 95% confidence interval is the mean value plus or minus 1.96 times the standard error. Remember that 1.96 represents 95% of the population data. So here we can see how the confidence interval is calculated for the data that we looked at earlier, and it results in a mean of 4, these are rounded up, with a 95% confidence interval of 3.9 to 4.2. So 3.9 and 4.2 are called the 95% confidence limits for the estimate, and the set of values between 3.9 and 4.2 is called the 95% confidence interval. So remember that that is what it is a confidence interval. Confidence intervals do not always include the true population value. In practice, we cannot tell whether our confidence interval is one of the 95% or the 5%. So now we can see why the normal distribution is central to parametric statistics. When we're looking at data that are measured on an interval or ratio scale and the data are normally distributed, then we can test to see whether there is a difference between them. So for example, if we have a control group, say for example people who haven't received a medication, and we have a treatment group, and we look at some measure like blood pressure, and we look at the distributions, we're essentially looking to see whether these sample distributions come from the same underlying distribution or whether we can conclude they are a different distribution, and that's what the t-test measures. The t-test assesses whether the means of the two groups are statistically different from each other, and this analysis is appropriate whenever you want to compare the means of two groups. The way that we calculate the t-value is have on the numerator the difference between the groups, and we divide that by the difference within the groups. So when the value on the top of the equation is large, or the value on the bottom of the equation is small, the overall ratio will be large. And the larger the value of t, the more likely it is to be statistically significant. To illustrate the t-test, I'm going to use the research question posed in this paper here called Communication about Smoking in Dutch Families, Associations between Anti-Smoking Socialization and Adolescent Smoking Relation Conditions. I'm just going to look at one aspect of the paper, and that is there a relationship between father's smoking status, so whether the father smokes or not, and if they have a constructive reaction to if they find out if their children have been smoking. I'm not using the actual data in the paper, I just made up some hypothetical data to illustrate the t-test. So the key thing is that the father smoking is the independent variable, yes or no, and parental reactions score is the dependent variable. So the higher the score on this measure, the more constructive the reaction is thought to be. So we're interested in seeing whether the fathers who don't smoke or the fathers who do smoke have a more constructive reaction. So we've got two groups of data, 27 in each group, and here are the data. So we have the fathers who don't smoke, they have a mean score of 29.9 with a standard deviation of 3.6. And the fathers who do smoke, they have a mean score of 27.7 with a standard deviation of 4.2. And the question that we want to ask is this a statistically significant difference? So we're going to use the data that we just looked at, again shown here, to calculate the t-value. And this is an example of an independent samples t-test because there are two different groups of people, father who smoke and father who don't smoke. And when we do the calculation, which I'm not showing in full here, we get a t-value of 2.083 and that equates to a probability of 0.04. So this is something that people sometimes get confused about. What do these numbers represent, particularly the p-value? So the p-value represents the probability of obtaining this test statistic by chance. Remember that this is a sample that we're looking at. What we want to know is how likely is this true of the population. So what this basically means is that there's a 4% probability that it's just due to chance. It's not a real difference. Another way of thinking about that is that there is a 96% chance that it is a genuine difference. So by convention, if there's more than a 95% chance that it's genuine, we would conclude that it is a real difference between the two groups that we are observing in this sample. Let's just imagine though that we did this test again with slightly different data, and this time we got a p-value of 0.16. What would that mean? That would mean that there's a 16% probability that this difference was due to chance, or conversely that there's an 84% chance that it is genuine. So that might seem like quite a large number. We've got an 84% chance to conclude that it is a genuine difference, but by convention we want to be 95% sure. So this is not enough to conclude that the difference between these groups is real. So in the example that we looked at, they were different groups of people. They were men who smoked and men who didn't smoke. So that would be an example of an unmatched test. But sometimes we look at the same people, for example, before and after taking a drug. So some statistical tests are designed to measure groups that are unmatched or independent. For example, is the admission blood pressure different between men and women? And some statistical tests are designed to test groups that are matched or data that are paired. So in other words, these are not independent observations because it's the same people. Is the blood pressure different between admission and discharge? So it's the same subject. So just remember that there are two types of tests depending on whether the data are matched or not. We're going to look at an example of a matched or paired samples t-test, and we're going to use some hypothetical data. This is from a study conducted to investigate the effectiveness of hypnotism in reducing pain. So we can see in the table that before treatment is matched to an after value, and we have a pain score shown here for each individual subject. And we have a study hypothesis, which is that the pain score will be lower after hypnotism. This is referred to as a one-sided test. However, we usually use the value of the two-sided test when we look at the output because we don't know for sure. It could be that the data will go the other way. If we have a one-sided test, we would miss that in any statistical analysis if by chance the data does go the other way. But I'm just going to illustrate it here for the time being. So we can see the scores before and after treatment. For this subject, subject 1, it's actually gone up, but for most subjects it's gone down. So we can see here at the end that the mean score before treatment was 8.7 and the pain score has gone down. So it seems like it's gone down quite a lot from 8.7 to 5.6. And here we can see the computation of the t-value. we have the different cases down here, that we have the before and after score. We subtract before from afterwards, we get the difference. We sum the differences, we divide this by the number of cases, and we get the p-value. In the old days, we would have had to look this up in a book of tables, but now using software, we can get the p-value directly. And because we were doing a one-sided test, all the probability is on this side. If it was a two-sided test, it would be split between this side and this side. So we can see that there's a very big difference between the two means. It's way over on this side of the curve, so it's a highly significant value. If we'd done a two-sided test, it would still have been, we would multiply this by 2, which would have given us a p-value of 0.019, which would have indicated a 1.9% probability that the difference was due to chance, or conversely, that there was a 98.1% chance that it was a genuine difference. So using this data, we can see that there is a genuine difference between the before and after pain scores using the data illustrated here. I'm now just going to illustrate how we would do statistical tests using software. In this case, I'm going to use the SPSS software that we will be using in our workshop. So we have two sets of data from different individuals, father who smoke and father who don't smoke, and our dependent variable is their reaction to finding out that their children smoke. So we're just going to look at that using SPSS. So if we were to use the SPSS software to calculate this, we would be selecting our independent samples t-test. We might have a data set with lots of different variables shown down here. The ones that I'm interested in are the dad smoke variable. That's my independent variable or my grouping variable. And the dependent variable is my outcome, which in this case is labeled constructive reaction. We'll be looking at the options in more detail in the workshop, but essentially this is what we would do, and we would then look at the output. Here we can see some of the output, and this is sometimes where people get confused by all the different numbers. So the first thing it shows us is the mean scores for the two groups of dads, those who smoke and those who didn't smoke. And we can see the means, the standard deviation and the standard errors that we've discussed before. And down here, this is the key bit. It shows us the t-value and the significance value. And as we said before, a p-value of 0.42 indicates that there's a 4% probability that the difference was due to chance, or conversely a 96% chance that it is a genuine difference. So we would conclude on the basis of this test that there is a genuine difference between the two groups. For a one-sided test, which SPSS doesn't show, we would take this value and divide it by 2. So instead of 0.042, we would have 0.021, which means that it would be even more significant. But remember that if we'd been predicting the opposite of our hypothesis, then we wouldn't have concluded that it was significant. So in most cases, we used the value for the two-sided test shown here. This time around, I'm going to show you a matched pair t-test, so we can see that the menu is slightly different. Paired samples t-tests. What we do is we select a pair of variables that are matched. So this comes from a study that I and my colleagues did in Stoke a number of years ago, where we asked people about the number of problems, financial, family and so on, that they had before and after they began to use drugs. And here we can see the output of that procedure. So the data look like this. We have the mean number of problems before and afterwards. So 3.5 problems before, 7.8 afterwards. So it does look like a big difference. The sample size was 103. Again, we see the standard deviation and the standard error. And here we can see the values for the t statistic and its associated probability. So we can see p is less than 0.001, so we conclude that there is more than a 99% probability that there is a genuine difference between the two groups. We'll have a review question. A researcher was interested in stress level of lecturers during lectures. She took the same group of 8 lecturers and measured their anxiety out of 15 on an interval scale during a normal lecture and again in a lecture in which she paid students to be disruptive and misbehave. What test is best used to compare the mean level of anxiety in the 2 lectures? Is it an independent samples t-test, a paired samples t-test, a one-way independent ANOVA, or a Mann-Whitney test? So which of those tests would be the correct test to use? So we asked a question about a researcher looking at stress levels of lecturers in 2 different situations, and it has a mean anxiety score, which is the correct test to use. So it's the same lecturers, so the answer is a paired samples t-test. What about cases when there are more than 2 groups that we want to compare? In this example, we have looking at different types of psychotherapy. I'm looking at their effect on people's self-concept score. We could do t-tests here. We could compare all the different permutations, but that would result in a lot of t-tests, and it would be difficult to interpret. So for that, we would use another procedure, which is called an analysis of variance. And an analysis of variance, the F ratio is the statistic used to test the hypothesis that the effects are real, that there are significant difference somewhere within these data sets, indicating that there is a significant difference. Analysis of variance does not assume linear relationships and can handle interaction effects as well. So the statistics can become more complicated depending on the research question that we're trying to address. Interaction effects are also something that we need to consider. Imagine a study that was looking at the effect of the amount of exercise people take in relation to how well they sleep at night. However, we also are interested to know whether that exercise was taken in the morning or taken at night. So the study is looking at the relationship between 2 independent variables, level of exercise and when the exercise is taken. And the dependent variable is the hours of sleep at night. And by graphing the data, we can look at the types of interaction, and this will help us to think about what type of analysis needs to be done. When we have 2 variables, looking at graphs is a good way of looking at interaction effects. And for each of these graphs, we can see the amount of exercise shown on the left and the right, light and heavy exercise, and the 2 lines indicate whether the exercise is taken in the morning or taken at night. So we can see in this first graph that there's a significant effect only of the time of day, not the amount of exercise. In other words, whether you take the exercise in the morning, for example, you will sleep on average about 6 hours. If you take the exercise at night, you'll sleep on average about 8 hours. But whether that exercise is light or heavy makes no difference. So there's a significant effect of the time of day only. Here we can see the opposite of that. It doesn't matter whether you take the exercise in the morning or at night. The lines are practically the same, but there is an effect of the amount of exercise. And there are many different types of interaction effects. This graph shows one particular type where the effects vary, whether it's according to the amount of exercise and the time of day. And in this one, so there are no main effects here, there's only an interaction effect. So what that means is that we just looked at the amount of exercise or the time. We wouldn't actually spot anything in the data, so we have to have an interaction term in the model. And here we can see that there is a significant effect in terms of the time of day. So there's this difference between the blue line and the green line. But we can also see that for the evening, there is also an effect of the amount of exercise. So even with two variables, the patterns can get quite complex. If you don't graph the data and only look at the summary statistics, you might miss these effects. We're going to have a review question on interactions. Imagine we wanted to look at whether enjoyment of guitar playing influences the relationship between the time spent practicing and skill level. How would we know if we had a significant interaction effect? So in order to answer this question, you need to think about what are the independent variables and what is the dependent variable. So the independent variables are the time spent practicing and enjoyment, and the dependent variable is the skill level. So we want to know if the independent variables interact in some way. So the correct answer is we would look at the interaction between the time spent practicing and enjoyment. We would see whether they were significant predictors of skill level. So the correct answer is B. So in this session, we've looked at some of the principles of statistical testing, and we've also looked at a couple of examples of particular tests. There are many, many tests, and we've only looked at one or two. But as always, the key principle to bear in mind is what is the research question being addressed. And this table here shows one way of conceptualizing it. There are many other tables which go into more complex scenarios. So that ends this session on the basics of statistical testing and inferential statistics.